Swayam Prabha. Digital India. Educated India.
See this, your dx and dy will have different sign. When you consider this length element ds, your dx and dy have different sign. You consider whatever your order is, direction of cyclic integration, say conventionally theta this, changing from here to here. So, in this case, for this part of the length, the way we have shown here, your x is decreasing, y is increasing. So, take that into account and then say what is e to the power I theta ds. Ds minus only I dy. Only I dy, no x. What is this becoming? Minus dx plus I dy, and what is that? So, this is minus dx plus I dz, sorry, minus dx plus I dy. What is that? Minus dx minus I dy. This is minus I dz. And then we put it here. What do we get then? X minus I y equal to
that, sir, how can we generalize the concept that for a part of curve x was decreasing and y was increasing? So, how can we
you take it for any other, if you want it other way also you take it, and in every way this is what it will come. This is just an example to see it, but you take whatever way you want and it will come to this. This is general, it is not that only for one particular case. what you do it for one case, ultimately it will come as the general case. You can try it anyway. So, it is ultimately coming as I rho by 2 W square d z. This gives the force exerted on a body by two dimensional ideal flow or two dimensional potential flow on a body, force exerted on a body by a two dimensional potential flow, general. This formula is known as Blasius formula. A similar formula is also present there for moment, but right now we will not do it. Now, considering the general complex velocity, in any case the complex velocity of any flow problem, as long as it is two dimensional ideal flow, will be given by this expression. Okay. May not be some term may not be present in a particular case, but any other term cannot come. The terms which are here, only some of them may come in a particular problem, but nothing new. They must be within this, must be a subset of this. So, this is the most general complex velocity. So, assuming this complex velocity, what will be this force? Considering the complex velocity, what will be the force? But first of all, look whether this function has any singularity. At z equal to 0. So, z equal to 0 is a singularity, and we are interested only in a integral over a closed encounter, closed curve, closed contour, and z equal to 0 is within that contour, or origin is within that body. So, if you remember that because of this integration, according to that residue theorem, only what is required? The coefficient of 1 by z, nothing else matters to us, only the coefficient of z. Okay. Now, anyway, the function is not w, but w square. So, think about w square. what will be W square, and we are interested only the coefficient in 1 by z, nothing else, because as we see from here, after the integration we will have only 1 by coefficient of 1 by z, that is what will give us non-zero integration, all other will give us 0. So, we are not interested to know what they are, only what we need is to square it and what is the coefficient of W z, W square z. Once again let us say we can write W square is C 0 plus C 1 by z plus C 2 by z square plus so on, and C 1 equal to how much? See, when you square this, the only z, only 1 by z term will come because of that product of these two, that is what is going to give us 1 by z, nothing else is going to give us 1 by z. Each of these terms will be square or they will be multiplied by 2. So, only these two will be multiplied and that will give us square. So, coefficient C 1 is only 2 B 0 B 1. And how much is that? B 0 is what? B 0 is what? Looking to this expression for complex velocity, B 0 is the constant velocity present or uniform velocity present in the flow, which is q infinity e to the power minus I alpha. That is the only term, only velocity which gives a constant velocity, q infinity e to the power minus I alpha, and B 1 1 by z. What basic solutions gives us velocity 1 by z? Those which have complex potential log z. Which has complex potential of log z? Source and doublet do not have complex potential log z. Vortex. The doublet, the way we have taken, has no log z. So, what will be B 1 in a general case and what will be B 0 in a general? B 0 in general case is q infinity e to the power minus I alpha, and what is B 1? B 0 is 2 q infinity e to the power minus I alpha, and B 1. m by 2 pi, m by 2 pi, and considering a clockwise vortex it is minus I gamma by 2 pi, m by 2 pi minus I gamma or m minus I gamma by 2 pi in general case, m minus I gamma by 2 pi. Out of that, if you remember that m, the source, usually gives, or source gives a flow field which is spherically symmetric, symmetric in all direction, symmetric in all direction. So, from physical ground we can consider or we can expect that source will not give any force, but source will not give any force, because it is not going to create any asymmetry anywhere, and force will be created only if the pressure is asymmetric. If there is no asymmetry in pressure, there will be no force, and since source gives a spherical symmetry, symmetry in all direction, the source will have no contribution and will neglect that part of source, and we will take only that I gamma by 2 pi. Okay. Now, that this force x minus I y is I rho by 2 into w square d z, which we know according to our theorem 2 pi I C 1, residue theorem 2 pi I C 1. So, that makes how much? I square minus pi rho into how much? Q infinity e to the power minus I alpha what it is coming rho
contribution of vertex will be minus I comma by 2 pi, minus I comma by 2 pi
in the
clockwise direction.
That is why we have taken clockwise direction, that we have the negative sign there, and in the force term we do not have the negative sign. That you have seen when we discussed about that circular cylinder. Or we can write it rho q infinity gamma e to the power minus I okay. Now, what is this direction of this force? What is the direction of this force? Looking to this expression itself, rho q infinity gamma e to the power minus I pi by 2 plus alpha. If you remember, q infinity e to the power minus I alpha was the free stream. Free stream was making an angle alpha to the x axis, and that term is represented by e to the power minus I alpha. This force is now e to the power minus I into pi by 2 plus alpha. So, what it is? In which direction the force is? This force is clearly perpendicular to that direction of the q infinity. We need not write even its real component and imaginary component, and all that is not required. From here itself we can say that this force is perpendicular to the free stream direction. and which is by definition is the lift force. Okay. And we can see again that it has now become general case that in a two dimensional ideal flow the force can be only lift force. We cannot have a drag force. A force in the direction of the flow is not possible. Of course, this is an unacceptable result, that force in the direction of the flow is 0 always, which is not true, is never true, but that is what a two dimensional potential flow gives. A two dimensional potential flow gives only lift force, not okay. Now, with this in background, let us now try to postulate some transformation which we can apply and get the flow over an airfoil from the known flow about a circular cylinder. Now, once again you know that whether we are in the circle considering the flow past a circle or considering the flow about an airfoil at far away from the body, that is in the z plane and zeta plane. Let us say in the z plane we have the airfoil and in the zeta plane we have the circle. So, both in the zeta plane and the z plane at far away, that is at infinity, the flow is undisturbed. Okay. The flow field is a uniform free stream far away, both in the z plane and zeta plane. Q infinity is same when z is infinity or zeta is infinity, meaning that once again the transformation function zeta as a function of z cannot have higher power of z, because if we have z, z square, z cube and so on, once again the velocity will not become same. So, any transformation we may think of, any complex function we may think of, it cannot have z square, z cube and so on. And so, the highest power of z in the positive side we can have only plus z, only z to the power 1. Okay. In the negative power of z, of course, we have no restriction, we can go to anything 1 by z, 1 by z square, 1 by z cube, as in the case of complex velocity. In case of the transformation, say like the transformation So, considering a polynomial or series as a transformation function, we can have only zeta equal to some z plus 1 by z or 1 by z square, 1 by z cube, anything we like. Now, of course, then the simplest will be z plus 1 by z, z plus 1 by z, that will be the simplest transformation, and this transformation or a similar type of transformation is called a Zhukovsky transformation, and which what we will study. You might say that we could have even simplest only z, why even v square by z? No, we need it, because see our airfoils will have a sharp trailing edge, we will have a trailing edge which is sharp or something nearly sharp, while in circle we do not have any point, any sharp point. So, we must have at least one critical point. If we just have z, if we just have z which do not have critical point dz df only at 0, for z we do not have any critical point on the surface of the circle, we will not have, but we need at least one critical point, so that we can have one point which may become a corner. We need one corner, an airfoil has a corner, a trailing edge. So, that is why you must have one critical point on the surface of the circle, and that is why at least this will give us a critical point, otherwise there will be no critical point. So, that is why this first term, hence it is simplest. We are not considering second, third and other terms, only first term is not possible, because that then we will not get an airfoil type of body, or we will not get any body which has a corner, but we need body with corners. Hence, this is the simplest transformation. These are the two reasons why our transformation is like this. This is of course not possible, we cannot have z square or anything. Here we could have 1 by z square and so on, but they will give more critical points and we are not interested in that. So, we are taking this is the simplest case, and also we do not want to make it complicated. And this transformation is called as Zhukovsky's transformation. Zhukovsky's transformation. In some book you may find this spelling also. This spelling is also available. In some books this is what is spelled. What are the critical point of this transformation? Critical points of the transformation. At critical points what happened? d zeta d z equal to 0. So, what is that? z equal to plus minus b. What happens to the angle at the critical point? Let us see, we apply this transformation to transform a airfoil to a circle. We are applying this transformation to transform an airfoil to a circle. Then what will happen to the angle at the critical point? Let us say one of these critical point coincides with the trailing edge of the airfoil. Let us say z equal to plus b, this point corresponds to the trailing edge of the airfoil. So, what is the angle at the trailing edge? The angle at the trailing edge let us say this is the okay. Think about these are the two tangent at the trailing edge and this is the trailing edge angle, we are calling the trailing edge angle to be tau. How much is this? This is the point corresponds to z equal to plus b. On the transformed plane, this must also corresponds to some point on the circle. So, let us say this is the corresponding point. Okay. This is what z equal to b in the z plane, and in the zeta plane it corresponds to some this. So, how much is this trailing edge angle tau? Consider two curve here, there is two segment of the circle just on the two sides of this point. We will take those are the two curves, and what is the angle contained by those two curves? Pi. At any point, if the two intersecting curve at any point on the circle, two intersecting curves, of course, they are part of the circle only, that in that sense they are intersecting, the angle made by them is pi. If this point would have been a regular point, here also the like these points and these points, they correspond to some of these points. Okay. So, the angle is remaining pi. What happened here at the critical point? The angle will be multiplied by n times, where n is the lowest order of the non-zero derivative. So, what is the non-zero derivative? Lowest order of the non-zero derivative? Yes, at z equal to plus b. You see the second derivative itself is non-zero. So, let us say this is, let us call it the angle, and this angle is become this. Okay. So, psi c equal to pi, then on the airfoil, or psi will make a confusion. Do not think it is a stream function angle. Psi f will be n into pi and that equal to 2 pi. Okay. Then how much will be tau? Tau is 2 pi minus 2 pi, 0. That is the trailing edge angles are 0. Okay. So, by this transformation, that is from using Zhukovsky's transformation, only those airfoils which have 0 trailing edge angle, they can be converted to circle, or the circles can be converted to airfoils with 0 trailing edge angle. The airfoils which have 0 trailing edge angle, they are called clasped trailing edge. That trailing edges are called clasped trailing edge. If the trailing edge angle is 0, it is called clasped trailing edge angle, clasped trailing edge. Unfortunately, however, all practical airfoils have non-zero trailing edge angle. A clasped trailing edge, then what the airfoil will look like? The airfoil will look like something like this. The two sides, upper surface and lower surface, are tangential near the trailing edge. But this is not what the common airfoils looks like. In the common airfoils, the trailing edge angle is a small but finite angle, not 0. So, most of the, or rather all practical airfoils are having finite trailing edge angle, they are not clasped. These Zhukovsky airfoils, they have clasped trailing edge. So, this is also you can say the Zhukovsky airfoils have clasped trailing edge. Now, what essentially this our transformation is? In the zeta plane, we have the circle and we know the solution of the potential flow about a circle, which is given by a superposition of uniform stream, a point doublet, which strength is given by the radius of the circle, and if there is a lift, then a circulation. If there is no lift, then circulation term is not there. But airfoils will in general give lift. So, or we are interested in lift, so we will consider that circulation. So, on the zeta plane we have a flow which is made up of a uniform stream, a point doublet which strength is known, and a circulation which strength is arbitrary. Now, this is the flow that we want to convert it to an airfoil. Now, essentially what is the conversion of a flow? A flow is say depicted by a certain flow pattern, some streamlines. What are they? A curve. So, if since we know the streamlines in the for the circle, we can convert those streamlines or transform those streamlines by this transformation, and they will become the streamlines for the airfoil. However, to do that, see we have certain free parameters. What are the free parameters? As far as the circle is concerned, circle has two parameters. The circle has two parameters, essentially two free parameters. One, its center and its radius. A circle has two parameters, a center and a radius. So, given an airfoil, we have to choose the appropriate circle, meaning we have to choose the center of the circle and its radius. Radius is of course, will be given then linked to the strength of the doublet, which we will see will be related to the chord of the airfoil. Chord, if you remember, the line that joins the leading edge and trailing edge, and so the leading edge and trailing edge, how to find the leading and trailing edge, that we consider the highest curvature and the radius of that curvature at the trailing edge and at the trailing edge side and the leading edge side, which will fix up the leading edge point and trailing edge point. Leading edge is all right, that is edge, but when you say which point, then it becomes a difficult question. Which point? We know, okay, this part is the leading edge part, we know this part is the trailing edge part, but which point is the leading edge point and which point is the trailing edge point, that may create a difficulty, and that is given by that the largest radius of curvature in this or largest curvature in this and the corresponding radius of curvature or the center of curvature, and similarly here also in this case of course, there is cusp trailing edge. So, no question of curvature, but in general case they are also that locate the center of curvature and join the two curvature and extend it. Wherever they intersect the airfoil surface, those are the leading edge point and trailing edge point. But anyway, the chord is the line that joins those leading edge point and trailing edge point by a straight line. Now, let us see that how will the velocity be transformed? How will the velocity be transformed? The streamlines, okay, we have got it. How will it transform? We know that streamlines we know in the for the circle. We can write the equation for the streamlines, we have already written, and then each point we can transform, okay, and we get the streamlines for airfoil. But for the velocity, how will the velocity be transformed? Velocity at a point in the circle is known to us, the complete solution is known to us. If the velocity is known to us, then what will be the velocity on the airfoil? Complex velocity on the circle and complex velocity on the airfoil. How are they related? Yes. On the circle plane, what is the complex potential? On the circle plane, which is zeta plane, what is the complex potential? Or say the complex velocity. Yes, the complex velocity is given by a free stream. The complex velocity is given by a free stream, a point doublet located at the center of the circle and a clockwise circulation. So, the complex velocity due to uniform stream is, we will consider a general uniform stream. For circle, see whatever the direction of the uniform stream, it is always towards a diameter, but the different diameter will represent different line as far as airfoil is concerned. So, we must differentiate that. So, we will consider a particular fixed x axis and the flow direction with respect to that particular angle. So, the complex velocity is due to a uniform stream, which is q infinity e to the power minus I alpha, the uniform stream contribution, plus a circulation I gamma by 2 pi 1 by zeta minus zeta naught. Once again, the distance is measured with respect to the center of the circle, where zeta naught is the center of the circle, plus a point doublet located at the center of the circle, and doublet strength is related to the radius of the circle. What is the complex velocity due to a point doublet? Complex velocity due to a point doublet minus q infinity r square e to the power I alpha by that vortex strength was how much? Mu equal to, what was that formula for mu? 2 pi r square u infinity, if you remember. That strength of the doublet was mu equal to 2 pi r square u infinity, or if r is the center of your circle, then the doublet strength must be 2 pi r square u infinity. So, that we have used q infinity r square and 2 pi on the numerator and denominator got cancelled. Here also there was on 2 pi, if you look back to the formula, and e to the power I alpha has come because this doublet axis is along the x axis. Okay. But we have considered a flow which is in alpha, making an alpha angle direction. So, there will be another alpha rotation for that. So, this is the complex velocity on the circle. On the circle plane, this is the complex velocity. What will be the velocity on the airfoil plane, the z plane? Our transformation is zeta equal to or z equal to zeta z. What will be the velocity in the complex plane W z? W z is okay. So, once we know the complex velocity at any point, we can find out what will be d z d zeta at that point and find the velocity on the jet plane or the airfoil plane. This is often expressed in this form also, that yes, huh? Oh, this is. We will now apply this transformation to certain cases, choosing those two free parameters at our will. We have already said that there are two parameters, the center of the circle and the radius of the circle, and choosing the two, we will see that what type of geometry we get. The flow field is of course obvious once we apply the transformation, but I think we do not have time. So, we will stop here today and continue this tomorrow.